In the last video, we rounded out our theory of constant coefficient second order linear homogeneous differential equations with our three different cases, really two, and one case is just a simplification of our two distinct roots if we have two distinct roots and a double root. And in this video, I'm going to do some exercises, which means getting rid of this and starting anew. So I'm going to grab an exercise out of my textbook and let's solve it. Okay, so I got this differential equation. Now let's think about how to solve this. So first of all, when classifying it, we notice, okay, we only have constant coefficients. So we only have constant coefficients. 4, -4, there's a 1 hiding there. Okay, so it's constant coefficient, it's homogeneous because it equals 0. So we know we can apply the methods that we just learned to solve this differential equation. Okay, so first we need to get our auxiliary equation. The auxiliary equation, or the characteristic equation, they're really just synonyms, same description here. The characteristic equation is 4 times our root r squared minus 4 times r plus 1. This must equal 0. Because we have this 4 here, I don't know if it'll be so fast to factor this, so let's just use the quadratic equation to get our value of r. In this case, r is going to equal, we have negative b, so negative 4 is plus 4, plus or minus the square root of negative 4 squared is 16, and then minus 4 times a times c is 4 times 1, 4 times 4 is 16. Alright, so it looks like we're going to be having a double root in this case. And this is all divided by 2 times a. It's 2 times 4, it's 8. It's a bad 8. I'll redo it. That's another bad 8. Alright, there we go. So, if we simplify this out, we get, alright, we know this is 0, 16 minus 16. So, finally, we get 4 divided by 8 is 1 divided by 2. This is r. So, we're going to be doing the case where we have a double root. And if we remember, for the double root, we used an almost sneaky technique to find another linearly independent solution to the differential equation beyond e to the, because there's only one r times x. So let's write down our solutions. So we know one solution is y1 is actually just e to the x over 2. So e to the 1/2 times x is e to the x over 2. That's one solution, but we can't use it as our second solution also because it's just the exact same. It would be linearly independent and our general solution wouldn't work. So our second solution, if we remember back, we can multiply our first solution times x to get a second solution. Y equals e to the x over 2 times x. And this times x is actually still a solution because r is a double root. We showed that with a lot of algebra in the double root video. And of course, it's still a solution, but it is now linearly independent, which tells us that the general solution, y sub g, is going to be some constant times e to the x over 2 plus some separate constant times x times e to the x over 2. And this is our answer. This is the general solution to this differential equation. And if you want to check it, you can plug it in. Each of these terms, the e to the, you'll take out the c because this has linearity, e to the x over 2, the x e to the x over 2 will all go to 0, and this is the general solution. Alright, I'm going to grab another problem. That was fun. Alright, perfect. I got another problem. Let's section off this area and write our second problem. So, it is going to be z double prime minus 2z prime minus 2z equals 0. And this time, I've got some initial conditions, which means even after we find our general solution, we've got a little bit of work to do, because our initial conditions are that z at 0 equals 0, z at 0 equals 0, and z prime at 0 equals 3. Okay, so how are we going to solve this? First step, just quickly, we should make sure that we're actually applying the correct technique. I see only constant coefficients. It equals 0, so it's homogeneous. Alright, we're good to go. So, first thing off, let's just set up our characteristic equation, we get r squared minus 2r minus 2 equals 0. Okay, looking good so far. So we're going to plug this into the quadratic equation because I'm not immediately seeing a factorization, and we're going to get r equals negative b, so plus 2, plus or minus the square root of r squared, which is 4, minus 4ac, which is minus 4 times negative 2, which is plus 8, because this term here is 1, and all divided by 2 times 1 is just 2. And this is going to come out to be 1 plus or minus the square root of 12, which is 2 times root 3, 2 times root 3 over 2. So we get that r equals, if we just simplify this out one last time, 1 plus or minus the square root of 3. Okay, so a little bit uglier than you might expect sometimes, but hey, we got a good solution. And what's more, these are two distinct and note also real roots. Two distinct real. So we can plug in our formula, which is just our simplest formula, the one that we got first. We get that the first solution is going to be e to the, and then r is 1 plus the square root of 3 is our first one, times x, and then our second solution is y2 equals e to the, and then minus root 3 times x. And then to get a general solution, we put these together. I guess I'll put it in blue. So general solution, we put these together. So we take scaled multiplication, so c1 times e to the 1 plus the square root of 3 times x plus c2 times y2, not equals, times, whoa, I don't know what I'm doing, c2 times y2 is e to the 1 minus the square root of 3 times x. Great. Well, if the question didn't give us initial conditions, we'd be done. This is our general solution. But the question did give us initial conditions, so we're going to have to plug them in. Very first initial condition we get is that z of 0 equals 0. Well, z is just our function, which tells us that at x equals 0, z equals 0. So, okay, one way we could write this also is instead of y general, we could write z general, but it's fine. So x equals 0, z equals 0. That tells us that the left-hand side equals 0. At the very same time as x is equaling 0. So we get c1 times e to the 1 plus the square root of 3 times 0 plus c2 times e to the 1 minus the square root of 3 times 0. Okay, but this is, when we multiply it by 0, this is just going to be e to the 0, and that's just 1, so we get c1 plus c2. So, okay, we didn't actually solve for c1 or c2 yet, but that's fine. We got a relationship, so if you remember this for later, c1 plus c2 is equals 0. Now let's try to glean a second relationship. Okay, well, it's telling us that z prime at 0 equals 3. Probably what we want to do here is to differentiate z so we can plug in when x equals 0 and make it equal 3. If we differentiate this, what we end up with is, and I'll try to switch colors to make it more visible, is that the general solution, the derivative of that general solution, and I'm writing small because I don't know how much space I have, is we're going to use the chain rule. So we're going to take down that 1 plus the square root of 3, so we're going to c1 times 1 plus the square root of 3 times e to the 1 plus the square root of 3 times x plus, and now we use the chain rule again, except on that. So we get 1 minus the square root of 3 times c2 times e to the 1 minus the square root of 3 times x. Luckily, this is big, but luckily when we plug in our initial condition, it's going to get significantly smaller. So z prime of 0 equals 3 tells us that when x equals 0, the z value, or the y prime, is going to equal 3. So we plug that in, we get 3 equals c1 times 1 plus the square root of 3, and again this e term is going to go to 0, plus c2 times 1 minus the square root of 3. This is all going to equal 3. So our second relationship is that c1 times 1 plus the square root of 3 plus c2 times 1 minus the square root of 3 equals 0. So now this is a bit of a strange system. It has some unpleasant numbers, but I think we can do it. Let's just box this off there also. So we have this system here, right here, and we want to solve it. How do we solve it? Well, somehow we're going to have to get it so we isolate just one variable. What we can probably do is, instead of dividing this second term here, we can just multiply in 1 plus the square root of 3 to this top equation, which will get us to, and let's restart right here. So we have c1 plus c2 equals 0, and c1 times 1 plus the square root of 3 plus c2 times 1 plus the square root of 3. That also equals 0. So if on this first equation we multiply 1 plus root 3, we get c1 times 1 plus the square root of 3 plus, and again, we're on this first equation, so we're going to get c2 times, and I didn't write this right, this should be a minus right here, 1 minus root 3. We're going to get 1 plus the square root of 3, and I'm not making a mistake this time because we're actually on the first equation, we're multiplying in 1 plus the square root of 3. This equals 0. Now we have something really nice here. If we were to subtract these two equations, this c1 term would go away. So we subtract it, we get c2 times 1 minus the square root of 3 minus 1 plus the square root of 3, but again we're distributing, so it's really minus square root of 3. And this all equals 0. And the 1's cancel out, which leaves us with c2 times negative 2 times the square root of 3. Yep. Equals, and I've been carrying the incorrect value here also. Just goes to show you have to really be careful with what you're doing. This is equal to 3. This is equal to 3, 3, and 3. I'm sure you've caught me on that already, and you're way ahead of me, I'm sure. Okay, so if we take this, what this leaves us with is that c2 equals negative, well, it just equals 3 divided by negative 2 times the square root of 3. Now, 3 over root 3, that's the same as just root 3, so we get negative root 3 over 2. This is what c2 equals. Alright, so we got one variable. Now, if we plug this in, we get that from this equation, alright, c1 minus root 3 over 2, just plugging things in, equals 0, which tells us that c2 must equal positive root 3 divided by 2. Alright, so now we have both equations. So now if we plug it in to our general solution, because remember, we actually did have, even though it's looking kind of messy, we did have two distinct real roots. If we plug it into our general solution, we get that the general solution for this differential equation is the following, is y general is some constant c1, but now we solve that initial value problem, and again, well, I don't know what I'm doing today, but this is c1. c1 is square root of 3 over 2 times, and then I'm going to have to actually go back up to remember what our roots were. Our roots were 1 plus or minus the square root of 3, which makes sense. Okay, so y general is the square root of 3 over 2 times y is, the first solution is e to the 1 plus the square root of 3 times x, and then the second solution is minus, the constant is minus the square root of 3 over 2, and the second solution is e to the 1 minus the square root of 3 times x. So hopefully you can see it is definitely nicer to have nice numbers, but even with some strange square roots flying around, we were able to get a general solution for ourselves. I will see you in the next video. Oh, wait, before I end the video though, I said general solution. I meant a particular solution to the initial value problem. Alright, I'll actually see you in the next video now.